of my work consisted in docking studies performed into a homology model of the 3D structure of the human PGP. So for the docking studies, I built a homology model because at the moment the crystallographic structure of the human one was not yet available in the inward-facing conformation. So homology model is a technique that let us construct an atomic resolution model of the target protein from its amino acid sequence and an experimental 3D structure of a related homologous protein. This is the so-called template. And in general, we need 30% sequence identity to have a successful homology model. For building a homology model, usually we have 4 steps that are to identify the templates from the protein data bank. Then we aligned the query sequence to the template structure. After this, we build a model based on this alignment. For building the model, we have the backbone generation, the loop modeling, and the side chain modeling. Then we have to assess and refine the model. Once if everything is okay, we have our model. If not, we go back to the selection of the template and repeat the whole processes. So once the model was built and assessed, the docking was performed on this set of 13 compounds, and the following general steps were followed. So for the docking simulations, first we have the ligand preparation. In this case, the charm force field was applied to the ligands, and then they were minimized using a minimization protocol in Discovery Studio. Then we have the protein preparation. In this case, also the charm force field was applied to the protein. It was energy minimized following a protocol in Discovery Studio, and the binding site was defined based on the ligand. Then we run the docking protocol. We used the CDocker protocol in this case. We score the docked ligand poses, and we calculated the ligand binding energy, also using a protocol inside Discovery Studio software. The ligand poses obtained, they were rescored with different scoring functions. Then we used the sum of ranking differences methodology for comparing the performance of the scoring function calculated. So based on the results of this analysis, then we selected the scoring functions to compute a consensus ranking scheme in order to select the top rank poses. So these are the scoring functions selected, and the operator used for fusing the ranking scheme was the geometric mean. Here we have the distribution of the selected ligand poses. They are colored in yellow in the homology model of the human PGP. On the other side, we have a view from the extracellular side of the protein looking into the internal chamber. The resulting poses, they were distributed within the transmembrane regions of the PGPs, showing interactions with protein residues of multiple transmembrane helices. During the development of this study, the cryo-EM structure of the human PGP in the inward-facing conformation became available, so we also performed the docking into this new structure as a validation of our model results. So the interactions of the ligands in the binding pocket in the homology model compared to those in the experimentally determined structure, they are in good agreement. The type of interactions for most compounds are equivalent in both docking studies, and they share many of the interacting amino acid residues. For example, here we have the top rank pose of cyclosporine A. It shows many interactions of hydrophobic character, a large number of P interactions, such P-alkyl interactions, with presence of simultaneous hydrogen bonds. This gives the complex a high stability, which is reflected in the estimated binding energy. In this scheme, the light green lines, they represent the carbon-hydrogen bond interactions, and the light rose, they represent the hydrophobic interactions. The residues that are colored yellow in this representation are the residues involved in hydrogen bonds. Here we have a 2D diagram of the same interactions inside the binding pocket. Here, in this other picture, we have the top pose of doxorubicin that forms many hydrophobic interactions in the binding pocket. The estimated binding energy is very favorable, and the stability in the binding pocket could be attributed also to the presence of hydrogen bonds. Additionally, doxorubicin may be stabilized by the presence of a P-sulfur type of interaction in the binding pose. So the main conclusions from this study are that the binding pocket consists in a big hydrophobic surface area. These results are in agreement with biochemical investigations, which concluded that the drug binding pocket is assembled mostly of hydrophobic residues, creating a lipophilic environment. From the analysis of the binding poses, we have that the large number of P interactions, together with the simultaneous presence of hydrogen bonds, it's important for the stability of the ligand-protein complex. We also notice that the hydrogen bonds present are mostly of weak character. For example, many carbon-hydrogen bond type of interactions. And some of the interacting residues observed experimentally in the mouse PGP crystal structure and in the human PGP cryo-EM structure were found to contribute also to drug binding in our homology model. And this demonstrates the consistency between the interacting amino acid residues predicted by molecular docking calculations and the co-crystallized data available. This work was published in June of this year in the International Journal of Molecular Sciences. So to conclude, the last part of my work consists in molecular dynamics simulations of the PGP with some ligands. This part of the work is not yet concluded, but I wanted to show a bit of what we are working on. We are performing molecular dynamic simulations on a set of 8 compounds. These compounds are compounds that are well known to interact with the PGP, and others that they don't interact with PGP, like pamidronate or busulfan. So for the simulations, we are using the recently solved 3D structure of the human PGP in the inward-facing conformation embedded into a POPC lipid bilayer. We are running simulations for 300 nanoseconds, and the starting configurations are the resulting docking poses from the previous study. For the simulations, we are using Amber 18 package. With this study, we expect to be able to assess if there is a significant difference between the molecular interactions of different classes of compounds, also to identify any motion patterns present, if any. We also want to evaluate the stability of the binding interactions within the binding pocket, and with all this information, try to shed light into the PGP transport mechanism. So I hope you can soon read our results in a net publication. So that's all from my side. Before, I want to thank you all for your attention, and I also want to thank my lab and my supervisor Marjana in Ljubljana for all the support during these 3 years of IN3. And a special thank you goes also to the IN3 family. So thanks for this great opportunity. And bye, and I hope to see you all soon.